In this segment, I want to talk about a couple of really interesting examples of wave interference phenomena. I just used that term, wave interference. Well, what does that mean? Previously, I've used the term constructive interference, and I've also used the term destructive interference. Recall that constructive interference happens when two waves have displacements in the same direction and the amplitudes add, and destructive interference happens when two waves have displacements in opposite directions and they cancel. Be careful, interference in everyday language has this meaning of getting in the way of. It has connotations of getting in the way of, like pass interference in football is getting in the way or messing up the pass. That's not really how we mean it here. Interference is simply what happens when waves combine. Sometimes it can be destructive and they cancel, and I suppose our colloquial connotations of interference work well there. But it can also mean constructive interference when the two waves add, right? And so that really doesn't jive with our sort of everyday maybe thought of what interference means. But both of those are examples of interference. And so interference phenomena is just things that happen when waves combine. And this is where things get really surprising. So here is one example. I have here a couple of cell phones. And on each of these cell phones, I have a tone generator app. I showed you the tone generator app in the Doppler video when I was showing you the Doppler effect. Well, I'm going to get a couple of tones going here, and we're just going to see what we can observe. Okay, so here I've started these cell phones. This is two sources, and they're each generating a frequency of 500 hertz. And what do you perceive? Well, presumably, you just perceive a pure tone, a continuous, unvarying tone. Now, watch what happens when I change one of the frequencies just a little bit. If you're like me, what you just heard was not two tones, not two separate tones, but rather one tone that wobbled back and forth. Observe one more time. I'll start them again. What you're observing are beats. What our brain perceives is the difference between the two frequencies and the average of the two frequencies. And so the two frequencies here were 500 hertz and 502 hertz. And so what does our brain perceive? We perceive a tone at 501 hertz, which has a 2 hertz beat. It goes whoa, 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 whoa. 2 times every second. It fades in and out. Observe again. If I change the frequency a little bit more, notice what happens. Whoa, 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 whoa. The beats increased. Again, we're hearing the difference. We're also hearing the average. So what our brains perceive is the average of the two frequency that wobbles in and out with a frequency that is the difference of the two frequencies. Let's look at this slide and see what that looks like mathematically. The beat frequency, what we heard, that wobbling frequency, it's just the difference between the two frequencies. So in that case, my frequency 1 was 505 hertz. The frequency on the second cell phone was 500 hertz. And so what we would hear is a beat at F2 minus F1 equals 5 hertz. And so what does our brain perceive? Our brain perceives the average of these two, 502.5 hertz, but we observe it wobbling in and out 5 times a second. That is what's called a beat frequency. So that was 505 and 500 hertz. Let's check out if I change it just a little bit more. Hear the beat frequency increasing. So now we're at 509 and 500. At some point, they become far enough away from each other that we no longer perceive those beats. Most of us now probably perceive two separate frequencies. I really don't know what's going on in your brain. That's what's going on in my brain. I can hear two separate tones right now. I don't hear one tone wobbling in and out. So we really only hear these beats when the two frequencies are quite close to each other. To understand how this phenomenon works, let's look back at the PowerPoint. Here in this picture, with the sort of red and the yellow waves here overlapping, we see waves from two sources that have frequencies that are close to each other, but not exactly the same. And notice what happens. They go from in phase, a loud sound, to out of phase, a quiet sound, to back in phase, a loud sound again. To say that another way, they move from constructive interference to destructive interference to constructive interference. How quickly does this happen? It depends on the separation of the two frequencies. A good example, and you'll notice this when you're driving around next time, is when you've got your blinker on and you're in the left turn lane and you're sitting there for a while. And your blinker's doing this. And the person's blinker in front of you is doing this. And then a minute later, they're synced up. They are in phase. And then a minute later, they're off. And then you wait a few minutes and they're back in phase. This is exactly what's happening with the beats, only it's happening very, very quickly. They're moving from in phase to out of phase to in phase. The nice thing is, the math behind this phenomenon is quite straightforward. We simply find the difference between the frequencies, and that is our beat frequency. Those of you who've ever played any music know that you can use beats to help you tune your guitar, or whatever instrument it is that you're playing. And you'll hear beats when things are out of tune with each other. So using some harmonics, which I talked about in a previous lecture, by exciting the M=4 mode on this slightly thicker string, and exciting the M=3 mode on this slightly thinner string, we can produce the same pitch. By playing them simultaneously, we should hear a pure, continuous tone when they are in tune. I do. I hear a pure, continuous tone. Let me make them slightly out of tune and see if we don't hear something different. You hear the wobble? That means it's out of tune. The beats decrease in frequency as I get it closer and closer to in tune. There at the end I had it in tune and we no longer hear the beats. A pure continuous tone. For this next example, I'm going to have to take you outside. We're going to venture out of the basement. Wish me luck. Okay, so I've brought you out into my backyard. And I'm out here because there's fewer reflections. In my basement, it's got, it's a fairly small room. There's a concrete floor, concrete walls. It's very reflective of sounds. And so it can be hard to hear some phenomenon. So what I've done, though, is I've brought my cell phones back out here. And we're going to get those two tones going again that are the same frequency. It's kind of annoying, I know. What we're hearing now is 1600 hertz. And we should hear a pure tone. We do. Two sources, pure tone. What happens if we move around a little bit? Okay, I hope that worked. I won't know until I edit this video. What we just observed was an interesting example of sound waves interfering. But this phenomena happens with all types of waves. We're going to spend an entire chapter talking about this phenomena happening with light waves. For right now, we're going to focus on the sound waves that we just observed, but you know what? It can happen with water waves too. And water waves are nice because you can just see them. It's easy to just look at them and talk about them. So let's check out this video here. This is from a YouTube channel called Veritasium, and it's great stuff. There's a lot of really interesting videos on this channel. Right here, what this guy is doing is he's got a couple of sources of ripples in a lake. So he's got these two balls and he's just bobbing them on the lake. And here you see he's just got one of them going, right? And so with just one of them going, we see the ripples spreading out in concentric circles. nothing surprising there. But watch what happens when he gets the second source going. We see an interesting interference pattern. What are we seeing here? We're seeing these lines right here where the waves combine destructively. This is destructive interference. Along this line here, the waves are canceling out. They are out of phase, and therefore they are canceling. And what I mean by they, the waves from the one ball and the waves from the other ball are out of phase at those locations. Therefore, they interfere destructively, and we see low amplitude. Along these lines here, we see high amplitude. The waves from the two sources here are adding constructively. This is constructive interference. They are in phase. It's quite an interesting pattern. And we see that it's a little bit stationary in time, right? We see these lines emanating out. Anywhere along these lines, we see large amplitudes along here, and along this line here, we see small amplitudes. This is exactly what we observed with the sound waves. As I moved the computer around, hopefully you noticed that the sound went from loud to quiet, to loud to quiet. We were moving from places where the waves were interfering constructively to places where the waves were interfering destructively. The reason I took us outside is because reflections from the walls screw up that pattern. So here he's showing the lines where they are adding constructively, and here on this video he's showing lines where they are adding destructively or canceling. Okay, so what we just observed was interference of waves. We're going to deal with it only in the simplest case of the interference of spherical waves, which is very similar to what we observed when we went outside. We just got to remember that all we're talking about here is waves adding constructively or destructively, creating a loud spot or a quiet spot. What determines the difference between adding constructively and adding destructively? Well, it depends on something we call the path length difference, right? So, my one speaker was here, my one cell phone, and my other cell phone was right here. If I had the computer microphone right here, then notice that that microphone is a different length from each of those cell phones. The sound wave has to travel a different distance to get to that point. So that means that when those waves arrive there, they might be in phase or they might be out of phase. Okay, to help us visualize this better, I'm going to employ a little bit of help. I've got my two cell phones here, my sources of the sound wave, and this is Christoph. He's going to help us understand about wave interference. My daughter loves Frozen. So do I. Okay, so Christoph is standing right here. Notice that Christoph is right in between my two cell phones, and he is equal distance from each cell phone. So I got my two waves here. These represent my two sound waves. So the cell phones are producing sound waves. They're identical sound waves. They are the same frequency. They're emitted from the source, and Christoph is the exact same distance from each of them. So what does Christoph hear? Christoph hears a loud sound because the waves are in phase when they reach Christoph. Notice the peaks align with the peaks, and the troughs align with the troughs, right? Peak with the peak, trough with the trough. Great. Christoph is happy. He is hearing a loud sound. Now, what I do is Christoph moves to a slightly different location. He moves over here. Now he's a little bit closer to this cell phone than to this cell phone. What does that look like? Let's see. Oh my goodness. He now is a little bit closer to this cell phone than to this cell phone. And so what does Christoph hear? Well, it's no longer the case that the peak lines up with the peak. In fact, the trough lines up with the peak, and the peak lines up with the trough. These waves are out of phase. Christoph now hears a quiet sound. So what determines whether Christoph hears a quiet sound or a loud sound? Well, it depends on the path length difference. It depends on the difference between these two distances. And we call that the path length difference. We're going to write that as delta R, and it's the absolute value of R1 minus R2. Now, If that path length difference is 0, then the waves travel the same distance and they arrive in phase. However, if the path length difference is 1/2 of a wavelength, in other words, one wave travels 1/2 of a wavelength less distance than the other, then they arrive out of phase. If the path length difference is 1/2 of a wavelength, then they arrive at Christoph out of phase, and Christoph hears a quiet sound. But it doesn't stop there. If they are one full wavelength difference, then Christoph hears a loud sound again, because once again, they are in phase. If the path length difference is 1 1/2 wavelengths, they are now out of phase again, and Christoph hears a quiet sound. 2 wavelengths, a loud sound. 2 1/2, a quiet sound. 3 wavelengths, a loud sound. 3 1/2 wavelengths, a quiet sound. I could do this all day until I run out of sound waves. Okay, let's take a peek at the PowerPoint and see if we can't, break this down into a series of steps. So, in order to determine whether we've got constructive or destructive interference, the first thing we need to do is we need to identify the path length difference. I could make that a tricky problem or a straightforward problem. It's geometry, though, essentially. You're finding what is the difference between these two lengths. Maybe this is 3 feet, maybe this is 2 feet. Great, your difference is 1 foot. Okay, we're going to do that. And then we're going to determine how many wavelengths that is. So in that case, you would need to know what the wavelength of your sound or of your water wave is. And then we determine how many wavelengths this path length difference is. So, for example, let's just say that delta R was 2 meters. And let's just say that lambda was 1/2 of a meter. How many wavelengths, then, is delta R? Well, we would divide 2 meters by 1/2 of a meter, and we'd say, oh, well, we could also write delta R as 4 wavelengths. 4 times lambda is delta R. So we're saying how many wavelengths is delta R? If this is a whole number, then we have constructive interference, we have a loud sound. If it is a half integer, in other words, 1/2, 1 1/2, 2 1/2, 3 1/2, etc., then we have destructive interference. It could be something in between, in which case we would neither hear the loudest possible sound nor the quietest possible sound. We would hear something in between, a medium sound. Now, I won't ask you about the details of that. My questions will be more limited to saying something like, is it constructive, destructive, or something in between? That's really it. Students tend to find these problems pretty tricky, but with practice, I know you'll get it. Let's do an example. So this example says you are standing midway between 2 speakers that are 8 meters apart. The speakers are emitting 686 hertz sound waves in phase. That just means they're identical sound waves. Part A says, are you at a point of destructive or constructive interference? Let me draw a quick picture and then we'll dive into this one. Here's a nice picture. Let's find out what the path length difference is. I've started out with a real straightforward one, haven't I? In this case, delta R, we'll go through each step though, equals R2 minus R1. Boy, that's 4 meters minus 4 meters equals 0 meters. 0 meters means the path length difference is 0. And so, the waves are in phase when they arrive at my eardrums and I hear a loud sound. This is constructive interference. B, is the sound loud or quiet? Well, if it's constructive interference, I will hear a loud sound. Part C, how far do I need to walk towards one of the speakers to reach a point of destructive interference? In other words, I'm looking for when is the path length difference equal to 1/2 of a wavelength? Well, first we need to figure out what the wavelength is. Without that, we can't do anything. So let's go ahead and do that first. We're going to use our standard big money wave equation. It looks like this. V equals lambda F. Lambda then is V over F. I've given us some nice numbers to work with. This is a 686 hertz sound wave traveling at 343 meters per second. And so my wavelength is 1/2 of a meter, or 0.5 meters. Okay, so now I know what the wavelength is. You might be able to just kind of reason through this particular one because it's fairly straightforward. But let's go ahead and set up an algebra problem. Because if you can't just kind of reason through it in your head, well, let's let the algebra do the hard work for us. I'm going to add a couple things to my picture. This is no longer 4 meters. Now we're over here somewhere. We're not quite sure where. So let's go ahead and call this distance here x. Since we know this entire distance is 8 meters, all right, let's add that to our picture, I suppose. We know this entire distance is 8 meters. If this is x, then this must be 8 meters minus x. And so we can now set up a quick algebra problem. We want delta r to equal 1/2 lambda. And we know that delta r is going to be the difference between these two things. So that is 8 meters minus x minus x. Again, it's the difference between the two things. Here's r1, here's r2. 8 meters minus x minus x. Okay, so let's just plug in what our delta r is. Now, recall that we found the wavelength was 1/2 of a meter. In order to have destructive interference, we need to have 1/2 of a wavelength. The wavelength is 1/2 of a meter. 1/2 of a wavelength, then, is 1/2 of 1/2 of a meter, or 1/4 of a meter. 0.25 meters is our path length difference. And now we can just solve for x. So I solved for x and I got 3.875 meters. Now be careful, that's not actually the answer that we're looking for. We need to read the problem carefully. The problem doesn't say, how far will I be from one of the speakers when I hear destructive interference? It says, how far do I need to walk? I was 4 meters from the speaker. Now I'm 3.875 meters from the speaker. That means that I had to walk a distance of 0.125 meters, or 1/8 of a wavelength. Pretty cool stuff.